Well, hello once again. I think we'll get the webinar started. Thanks for joining the session today. My name is Wayne Hesh. I'm the product manager for Visual MODFLOW Flex here at Schlumberger. I appreciate you taking the time to join the webinar today. It shouldn't take any more than 30 to 35 minutes. That was the duration of the session we did last week. The main focus today is to review some of the developments we've done with version 2013.1, highlighting the addition of support for MT3DMS and the numerical modeling workflows. If this is your first time using WebEx, just a few brief comments. You can use the chat feature, which is located in the WebEx toolbar at the top of your window for questions or comments. If you have detailed questions, please leave these till the end. However, I'll try and do my best to answer questions for you throughout the session. If I'm unable to answer your email, just feel free to email me. Answer your question, feel free to email me at any time. My address is shown on the screen there. And we'll be recording the session today and make this available for download on our website or on our blog in the next few days. The outline of the webinar today is the following. We'll discuss the addition of transport using MT3DMS, go through the workflow, how you can handle working with multiple transport scenarios within your Visual MODFLOW Flex project, highlight the improvements in the performance in transport in Visual MODFLOW Flex over the classic Visual MODFLOW, and discuss how we handle bounding conditions or sink sources for MT3DMS. Also highlight the additions, the improvements we made to the numerical modeling workflows, and then leave it open for questions at the end. Before I continue, I should mention that I won't discuss MODFLOW USG in this webinar today. We have an initial webinar coming up likely in September, October that highlights MODFLOW USG. There was a few questions about that in the session last week, so I thought I'd mention that up front today. So the way we set up transport in Visual MODFLOW Flex, we tried to follow the workflow that you're familiar with in Visual MODFLOW Classic, which starts with defining your objectives. So you define your sorption and reaction types and the corresponding default parameters. Then define the properties, so your initial concentrations, species parameters, etc. Define your sink sources or your transport boundaries. Define your observations. Define the run settings, such as the advection method, the frequency of output times, etc. You then translate and run, and then you can analyze the results. You'll see the workflow is also similar to the building a flow model, with the exception of the sorption and reaction options. So transport inputs are defined in the numerical model in Visual MODFLOW Flex. These numerical models can originate from several sources. You could import the MODFLOW dataset or a Visual MODFLOW project, which contains the flow parameters, and then define the transport inputs on top of that. Or you may have an existing transport model you want to import and adjust, and I'll talk a little bit more about that later on. You can create a new model using the Create Grid option now that we have in version 2013. Or you can convert an existing conceptual model to a numerical model, then proceed to define the transport parameters. There's significant benefit in having transport defined alongside a conceptual model and following the conceptual model features in Visual MODFLOW Flex. These are highlighted in the next couple slides. So you can do reliable QA and QC of your transport inputs and results to existing borehole data, for example, correlating plume locations to borehole data, also your monitoring locations and your geological model. Keep in mind that Visual MODFLOW Flex lets you import and interpret and display any raw data in 2D or 3D, including XYZ points, which you can render by observed field concentration. You can load cross-sections from Hydrogeologic, or you can also generate your 3D geological model and do slices and cutaways, etc. This also provides effective visualization of contaminant concentrations in a number of different views, including a plan, cross-section, or 3D views, and you can also do animations. The other nice addition we've added in VMod Flex is that you can deal with multiple model runs, and this is true, as mentioned in previous webinars, for the flow model, but in addition, it's also true for the transport runs. So if you have an existing model with inputs and outputs, you can clone that, what's called a model run, or duplicate it. It'd be similar to doing a save as project previously with the Visual MODFLOW Classic. The difference is that these multiple model runs can all exist within a single project, so you don't have to flip back and forth between different versions of a model. So this makes it very easy to adjust different transport parameters or properties or what have you, the evection method, for example, run the transport model and see what impact that has on the results and compare those results to different model scenarios. A simple example on the screen shows different dispersion parameters for the same numerical model and the corresponding results, which you can compare side by side, or you can also calculate the differences between those model results. So as mentioned, you can have any number of transport model runs in your project. You can calculate the differences between the UCN files from the different runs and plot those differences in 2D or 3D views. Again, it makes it easy to evaluate different scenarios such as remediation schemes or pump and treat scenarios or pumping rates or pumping locations. Any number of variables you want to adjust can be done quite easily within the Flex environment. And it makes it easy to do and streamlines uncertainty analysis as well. So the picture on the screen shows the differences between two transport models by simply adjusting the dispersion parameters. So you can see what impact that has at the plume concentration down gradient. This can be plotted in 2D or as contours or also in 3D view. The other big benefit we have in VMod Flex is the ability to compare various numerical grid discretizations. So if you worked with transport models before, you know that the right grid resolution can have a significant impact on the numerical dispersion or the accuracy and the run times that you have for your transport model. So if you build your flow model in a conceptual model approach, this allows you to evaluate several grids for your transport models with different horizontal and vertical discretizations. Thereby, you can minimize the numerical dispersion and find the ideal balance between models that don't run too long, such as several days, but still provide enough accuracy in the areas of interest. This is possible as well when you create newly created numerical models. As I'll show you later, when you digitize properties or boundary conditions, you create a conceptual version of that, allowing you to convert that onto additional numerical grids should you decide to evaluate different numerical grids. The next couple slides show a little test we did with this. It's from the same conceptual model, the first with 3 different numerical grid representations and the impact that it has on the concentration observed down gradient. So with a very coarse grid, naturally you're going to get numerical dispersion. This is just a grid of 100 by 100 by 3 layers. And we added a compliance point down gradient. At this location, we measured the concentration of around 240 milligrams per liter. I think this was just benzene in this case. As you increase the horizontal discretization but keep the same vertical discretization, you'll see that that observed concentration drops down to 143. And the last example, we had further horizontal discretization. In this case, refined the upper layer where the contaminant source was being added by a factor of 3. So by changing both the horizontal and vertical discretization, you can see now that the observed concentration at that compliance point now measures 5.7. So a significant difference over the original 240 milligrams per liter. So again, this type of demonstration shows you that it's very possible quite easily to generate several numerical grids. You can find which one is the most suitable one for your objectives and then use this one for your calibration moving forward. The other big improvement in VMod Flex over the classic environment is in the performance, and the next 2 slides will discuss this. The first is the actual run times. So the fact that we use a 64-bit version of the MT3DMS engine can have a significant improvement on the run times. And in general, we use executables in VMod Flex instead of a DLL version. So the DLLs in VMod Classic were a little bit slower, and also since we visualized some of the runtime, real-time run results, it slowed down the overall engine run times. So with the executables, we can see pretty good improvement in the runtime. So with this transport model that had around 600,000 cells and 15 stress periods, you'll see in the VMod Classic environment, it took around 5,000 seconds to run. And with VMod Flex, with both the 32 and 64-bit versions of the engine, it's roughly half that. So you can see pretty significant improvements in the runtimes in VMod Flex with MT3DMS. The other thing that's possible now is that you can run these larger transport models. So by having the 64-bit version of the transport engine, you won't get any issues with running out of memory. So with VMod Classic, since it was a 32-bit application, we only provided the 32-bit version of the MT3DMS engines. In this case, when you had large transport models, in this case around 5 million cells, you may have received an out-of-memory error message with that. So you shouldn't get that with VMod Flex, since you can run the 64-bit version of the transport executable and allows you to take advantage of as much memory that you have available on your machines. So we did some additional benchmarking in this case with a larger transport model. The resulting UCN files were 1 gigabyte. What we did for this one in VMod Classic is we ran the MT3DMS executable outside of Classic, as I mentioned, since it wasn't possible to run it within VMod Classic. And we just want to demonstrate how much better the visualization and the display and drawing times were in VMod Flex over the Classic environment. So the table at the bottom there shows the different display options showing color shading and contours of the resulting contaminant concentrations. You'll see with the changing the layers in VMod Flex, it's roughly done in half the time. Change the output time is done quite quickly as well. There's a significant improvement when you're showing contaminant concentrations along cross-sections, so a selected row or column. You'll see this can be done quite quickly in VMod Flex. And the same is true when you're zooming in to areas of interest or zooming back out to the full region. This is done very quickly within VMod Flex, whereas in the Classic environment may have taken anywhere from 6 to 12 seconds. This was done on a Windows 7 64-bit machine that had 8 gigs of RAM and a dual-core processor. I'll do a quick live demonstration of the performance shortly. A quick remark about transport boundaries or sync sources and how we handle these in VMod Flex over VMod Classic. So in Visual MODFLOW Classic, the transport boundary conditions were defined separately from the flow boundary conditions. So you had, for example, a recharge, evapotranspiration, concentration. Point source had to be assigned to existing cells that had flow boundary conditions. And then there was also a constant concentration, which is its own special case. It can exist on its own. It was a bit confusing to carry that approach into VMod Flex. And just in general, since the sync sources are typically added to flow boundary conditions, it was really unnecessary to have to redigitize those cell geometries on top of existing flow boundary conditions. In most cases, those time schedules for the transport boundaries are consistent with what's being used in the flow model. Having said that, you can define different time periods for the transport boundaries in VMod Flex. So for that reason, we decided to merge those boundary conditions merge the parameters from the sync source boundaries into the existing flow boundary conditions. So the sync source parameters, which are just time and species concentrations, are now defined as part of the flow boundary conditions. This is done when you add, so you can add your species concentration while creating a new boundary condition, or you can edit existing boundary conditions and change those default species concentration values over. If you have transport turned on, by default, these species concentrations will show with a value of -1. This indicates that no mass is being added to that flux. And just to remark that that's not the same as a species concentration of 0, so be sure not to confuse those two. Again, we still have a specific option to define constant concentration because it's a special case since it can exist on its own. A few screenshots that show what those boundary conditions look like in VMod Flex. So you'll see when you're editing a river boundary condition in the top right there, if transport is enabled in your model, you have an additional column where you can define the species concentration, which can be steady state or transient. Same is true for well in the middle of the screen. you have your well rate that's shown as the first row in the table. After that, you have your concentration, which can be defined. And lastly, when working with recharge or evapotranspiration zones, these have a database view similar to properties for hydraulic conductivity, for example. So in the database view, when transport's enabled in your model, you'll see an additional column for species concentrations. In the example in the bottom right there, you'll see for zone 2, the default value is -1, which means no sink or source is being added. But in zone 3, the value is 5,000 for that set of cells. All right, I'll do a quick demonstration of the transport workflow now in VMOD-Flex. Just to recap, I'll collapse this a bit. So I'll go over just the workflow and what the changes you'll see in the GUI and how we try to keep things as similar and consistent with what you've done in VMOD Classic for several years. So you start by defining the modeling objective. This display on the right here looks very similar to VMOD Classic. You can turn transport on or off, specify your sorption and reaction options, and then in the lower table you have your default parameters for species and model parameters. These will change based on which selections you choose in the upper part of the grid here. At the define property step now, when you have transport turned on, you'll see additional parameters that are added to this drop-down list. So in addition to the flow parameters, you now specify initial concentration, which is done for each species that you have in your model. Specify the dispersion, species parameters may be on or off depending if you have reaction enabled, and then your bulk density. So these parameters are similar to what they're the options for these parameters are similar to what you have for the flow parameters. You have a database view. You can assign using a polygon or polyline. You can see these rendered by cell or by color shading. And as you mouse over, you'll see the parameter values in the status bar at the bottom of the screen. The boundary conditions, I'll show you how that's handled now. So we choose a river, for example. If you were to edit an existing river cell, you'll see now when transport is enabled, you see your flow parameter at the top of the screen, and at the bottom you'll see now a concentration species, which can be, you have by default the value of -1. You can change that to any value that you wish and enable that. In this model, this is actually a replica of the airport model that's available with Visual MODFLOW Classic. So in this model, we have recharge concentration defined, so I'll turn that on. So we have 2 recharge zones, and for recharge zone 3, here's that species concentration that we added to that set of cells. At the define observation well step, you can now add your concentration observation points in addition to your head observations. These are shown in orange and will also appear on the tree on the left side here. Aside from that, the workflow hasn't changed up until when you get to the translate step. So when transport is enabled in the selected engines at this step here, when you proceed to the translation step, you have now your additional settings for MT3DMS. So your porosity options, your advection method with the option to use or exclude the GCG solver, and then your output control options. So your simulation length, the number of transport steps, and then this screen here you specify where you want output times to be saved at. If you have these defined in the, if you have a lot of output times defined in the text or an Excel file, you can paste those directly into this grid quite easily. Once the translation is done, you can translate the model, proceed to running, which is pretty quick for this example. Once the model run is complete, you'll notice that we made a few changes to the tree in the bottom left here. You now have outputs separated by flow and transport. So species concentrations will be added under the transport folder. You'll see one item in the tree here for every species that you have in the defined in the modeling objectives. So you can turn on the concentration, You'll see here your output times that you define, which you can flip through quite quickly. As you change, you'll see the color legend appears, and color legend will update on the left here. You can span through multiple layers. As I mentioned previously, they're showing things along a cross-section or a selected row or column is quite quick now. Try row number 9. Yeah, so you can see how the performance is. This is a very simple model, but you should see significant improvements even for the larger models, that you don't really get those bottlenecks that you would have had sometimes with the classic Visual MODFLOW. And lastly, you can show the results in a 3D view quite quickly. By default, it'll show a color map. Again, you can adjust the output times. And if you load the concentration results into a standalone 3D view, you can show an isosurface. If you click on View Charts, you should see options for transport plots, where you can plot your observed species concentrations to your calculated concentrations. You have different filters on the left here for showing different species, filter by layers, so show only concentrations that are, show only observations that are in a certain layer. And then within each layer, you have the corresponding observation groups. So you can, similar to classic Visual MODFLOW, you can change between calculated versus observed or your time series plots. If there's any questions, feel free to use the chat option. I'll do my best to answer them at this time. Otherwise, we'll keep chugging along on the webinar. So the other improvement we've made in this release is now you can create new grids and follow a traditional numerical modeling approach similar to classic Visual MODFLOW. You start out by create a new project similar you would previously, and then choose the numerical modeling approach, and then choose the option to create a grid instead of import a model. You can define your grid size, the grid spacing. You can use a polygon that you've imported, a shape or DXF file to define the model origin and the XY spatial extents. So there's a couple of nice improvements we've made to these features over the classic Visual MODFLOW. When you define the number of layers, you have different options for defining those layer elevations. So you can define a constant value resulting in the flat layer elevation, or for each of the layers, you can specify a surface that you've imported. So if you've imported a surface from a DEM file or an Esri ASCII grid, you can map that directly as the specified top or bottom for a surface, for a layer, and then combine any number of surfaces or constant values below that. The other thing you can do with this, with the addition of this option now, is you can create simple models for local grid refinement, so you don't have to follow a complete conceptual model approach. If you have a very simple example where you want to, for example, look at drawdown around a pumping well from a pumping test, you can just create an empty grid, define a child grid around the area of interest, draw your simple boundary conditions using the digitizing tools with Polyline and Polygon, and then run and view the results. So I'll do a quick demonstration of those options now. So I'll create a new numerical model. And when you get to this option now, you'll be able to click on this Create Grid Op button here. And I'm just going to collapse that so we can see all the options. So you have the option to specify the grid size and the spatial extents, as I mentioned, the min and max X and Y. Here's where you specify if you have an imported polygon or polyline, you can just grab that from the tree and assign it here. And in the bottom of the screen here is where you specify how many vertical layers you want in the model, and for each of the option, each layer, top and bottom, you can specify a constant value or use a surface. So I believe I have a surface from this one. If I want to use a surface, I just turn this checkbox on. I grab a surface data object that I've imported or created by interpolating XYZ points, and I add that to the display here. and then I can adjust any of these other remaining layers as I need to. Create the grid and proceed on, and now I have my corresponding grid that's created. So you'll see here's a cross-section along the specified row. The top of layer 1 follows that surface, and the layers below have those constant layer elevations that I defined. After that, you can proceed on to digitizing properties and boundary conditions as you would with classic Visual MODFLOW, assigning using a polygon or to the entire layer, digitizing your boundary conditions, assigning wells, etc. A few remarks on some of the other improvements we made in this release. We've improved the management and selection of workflow windows and viewers with a tab approach across the top of the screen, and you may have seen that in the previous slide. I'll show you that in a second. We've also added an option to adjust the layer order when you're working in the 2D layer view, so you can move layers up or down or to the top or the bottom. These are saved as you proceed back and forth between the workflow. And you can also view and edit the pumping well attributes in the numerical model workflow when you're defining your boundary conditions. So these are these tabs that I mentioned that we've added in this release. So when you add new 2D or 3D views, these are now added as a tab instead of across the bottom of the window. So it makes it easy to flip between display of different data objects, go back and forth between working with your numerical model, which is defined in the workflow here, and just viewing your raw data or your interpreted results in 2D or 3D. These tabs can be reordered. You can do vertical and horizontal grouping, and they can easily be closed, such as shown as here. You can also reposition them. It's very flexible, and I find it much easier to work with and switch between windows than what we had previously. The other option, which I'll show you, is the layer order. So let me go back to here and turn off recharge. In the layer views that show the numerical model data, whether it's the input or the results, you have now this option to reorder the layers. So if you have shapefiles or air photos, images, etc., that you want to appear at certain positions in the layer view, you can now load this window. It'll show you all the so-called layers or data objects that are displayed on the screen at the current step, and you can reorder the position of those. So you can move things down to the bottom, to the top, etc. So this is possible at the define property step when you're working at the boundary additions, and also when you're viewing the results. You should see this option there. Yep. The other option we've added is when you're defining your boundary conditions, if you choose wells, you can now edit existing pumping well parameters. I don't believe this one has any in there, so let me just add these in quickly to show you how that works. So the well cells are located in layer 3 in this model. And when you're working with wells, you can now edit a single pumping well cell and see the corresponding pumping rates. Here you can see also, since transport is enabled, you have the option to add a sinker source to that existing flux. So some of the things that we're working on improving for future releases and the limitations to be aware of. If you're working with MODFLOW LGR, this is something that is not supported, transport. So MODFLOW LGR does not support MT3DMS. It's a limitation of the USGS version, not something that we've added in VMOD-Flex. We haven't implemented all the advection methods quite yet, so we've focused on the key ones. So the upstream finite difference, TVD, and central finite difference are in there. We don't have support for the particle-based methods, so MOC, HMOC, etc. If these are something that are interested to you, then please let me know, and I'll do our best to get those out in a future release. If you're importing an existing VMOD Classic model with transport, the properties and the reaction parameters will be loaded. However, the boundaries and the calibration data will not be imported, and this is something that should be available in the first patch, which should be available in the next couple weeks. So in this case, you just need to reassign your sink sources in VMOD Flex and bring in your concentration observation wells from a file that you've exported from VMOD Classic. I've done it with a few models. It doesn't really take very long if you get stuck with this, and feel free to email me or our tech support group and we can walk you through that. We don't have a full representation of transport in the conceptual modeling workflow. That's why earlier on in the webinar I highlighted that transport is assigned to the numerical model. This is something we're still also working to fill in the gaps. So if this is something that is of interest to you, please let us know how important that is. As I mentioned, the bounding conditions are defined for both the conceptual and numerical model, however, the properties are not. We're working on adding support for pests to optimize transport parameters, and then the next phase will be adding support for reactive transport for RT3D and or CWAT. Both seem equally important. Please feel free to send me your comments on which ones are more important to your projects, and we'll do our best to get those in there shortly. The next webinar we'll be doing will be likely in the fall here in Canada, so around September, October, and we'll focus on MODFLOW USG. There's been quite a bit of interest in this, which is to be expected. We had a lot of traffic going to the blog posts that we did on our website. I did a presentation at the MODFLOW conference a few weeks ago, and there was quite a bit of interest in the grid geometry that we're using. If you haven't had a chance to take a look at what we're doing with MODFLOW USG, please take a look at our website and the blog post we did earlier this week. So we just want to get that working a little bit better in the software, and once we have something that we can demonstrate, then we'll plan to do a webinar on that. If you have any questions or suggestions on MODFLOW USG, please feel free to contact me. So for more details, you can visit our website, or as I mentioned, email myself or our sales group. And at this point, I'll open up the chat option for questions that you may have.